Okay. Okay, so today's agenda is so I'll get into the agenda for a second, but I wanted to talk about the logistics because we are actually pretty close to the deadline for project submission. Today is 28th, and project report submission is due next Wednesday, right? So today we'll try to kind of keep the discussion. I think one of the discussion points was about Spark. I think most of you have done Spark before in 561, right? So most of you have probably done it. If not, we'll discuss it, obviously. And correct me if I, don't go over something correctly. So we're going to look at Spark and then Kafka as two examples of two different types of distributed computing. But that's just get a flavor of some of the things that people do in practice. So more importantly, next couple of sessions, we have presentations in person in the class. So you should be present. So there'll be attendance for everything. But mostly you have to support your teammates who've actually spent some time exploring a tool. They're gonna talk about what they've learned and what they've seen. So how we divided this presenting on 55? Yes. So again, this is a choice I just thought about, which is we will make a randomization in class at the beginning of 5th. So we all have to come prepared. You have to be prepared of presenting anytime. Okay, that's for fairness. I mean, otherwise, a bunch of teams will get an extra week to prepare. And it's also, you finish and then you're done, right? I mean, you don't have to prepare again as long as you remember it. So that's the plan. Okay, it's a good question. I was just gonna mention that because the way we'll try to do it is I'll try to set up a box folder so that all of you can upload your slides in whichever format you want. Instead of previous semesters, I've tried using just Google Sheets and people inserting their slides. So this time I'll try something else. I'll send you an announcement to Blackboard. Okay, so I haven't sent pretty much any announcement to Blackboard, but there is an announcements tab in the Blackboard on the top left. I'll send one with the link to the place where you can upload your presentations. I mean, that's not it's not a submission deadline. It's mostly for it's going to be hard if you want to switch, use your own machine and connect your HDMI cable and all that. So you should just download from there. I mean, I will download from that box and you can just play it through my account here. Okay. I mean, you can use the slides from my account here. For the report that is there like a format of what you want us to cover in the slides? Depends on the tool. Every tool has a different, I mean, there is, right? So there is a project thing which is mentioning like, I mean, it's actually very generic. I mean, there is an example, okay, but this example is, I really don't want to, spend too much time on the example because that's very specific to, I guess this is not the example, but it is mentioning some of the pointers, right? What are the components? Snippets of like how we created the environment and like maybe a snippet of course. If you have an environment to create, yeah. I mean, some tools don't have anything, right? Okay. Yeah. Yeah, so that's why I didn't want to kind of get into every bullet point here because they're not applicable for first three are kind of yeah, some of them are, yes. I mean, many of them are, but some of them are like there may not be a Jupyter notebook involved. Is it project plan necessary? I mean, if you're doing it overnight and only like take a couple of hours, probably not. Break up of like by what day, schedule time. I mean, if you're asking this question now, we have 3 weeks left. Or no, max 3 weeks left, right? So, sorry, there's only 1 week left. Yeah. Actually. Sorry, I was thinking of the presentation, which is 3 weeks from now potentially. Yeah. No, it's not needed. I mean, this was just I mean, if you actually did it, you should actually, so all projects, and you'll see, I mean, they may not be doing Gantt charts and stuff, but you have to plan your project, right? You have to have some estimate. You will probably cross it. You might not be true to the, you might overestimate or underestimate, many things can happen, but you need to have a plan and then execute and then realize that you're not, right on target perhaps, and then adjust accordingly. That's just a simulation exercise in a classroom setting, but in real world, sometimes there is no repercussion. Sometimes the whole team can get laid off. Okay, so just to this was just a point that I added there, just to if you're doing it, then you should add it there.
And how long is the presentation? Approximately.
Okay, so that's a good question. I think is there no information? I'm trying to recollect the number of teams,
19.
which I just closed the tab. 19 teams. Oh wow, that's like 9 presentations or 10 presentations per session. 7 minutes.
7. This includes the question answer.
No, 7 plus 3 for questions. But if you don't finish in 7, then that's the sharp cut. Okay, so you can't take extra minutes and eat into the question answering time. And if there's no questions, that's not a big deal. We'll move on to the next thing. So I'll keep the time pretty strict. Okay.
So can we push the deadline to Thursday?
Yeah.
Which deadline?
Like Thursday before class.
4th is Wednesday, so can we just keep it with that's
okay. So can one of you send me an email? Yeah, just send me an email during the break or now. I can just. So is everybody okay with it? First of all, I know 2 people said they want. The point of like having a deadline earlier is so that you have some time to actually make the slides. Okay, if you're going to write the report and do the slides at the same time, you are putting more pressure on yourself. Okay. So how many of you are not in favor of moving the deadline to right before the class, the project upload? I mean, I don't see a strong support for having it right before the class. You want it? Okay, who wants the deadline to be moved to Thursday, 5 p.m.? Extra minutes for just the project report. That'll eat into your presentation preparation. Okay, and if the presentation is bad, then that kind of reflects badly on you. So okay, people want extra time. You may think there's an optionality where there's nothing to lose, but there is something to lose. Just think about it. You can submit it before also, even today, if you have already done. So it doesn't. That's fine. Sure, I can just send in an email. I can move it to 5 p.m. On that day. Okay. So yeah.
The time says 20 minutes. Can we do 15? I think that'll be enough for everyone.
What is?
It says 20 minutes.
Where does it say? Oh, that's wrong. I just said 7, right? So where is 20 minutes here?
Can we make it 12 minutes and 3 minutes per question?
He just said 7 minutes per item.
I mean, it's 2.5 hours, so divided, that's 150 minutes divided by 10 teams.
Okay, so where does it say 20 minutes? It doesn't say 20 minutes anywhere. Oh, okay. Oh, that was before this this larger number of teams. The number of teams, if it was 12 or something, that makes sense. But it's like 20 teams here. Yeah, this I need to edit. Actually, since I'm on GitHub, I can just edit it. This is gonna look bad, but let's see. Okay, I don't want to commit to a time here and then forget about it next time. Each time.
12 minutes. And then 3 minutes.
No, we'll provide a walkthrough. That's it. Provide a walkthrough, and I will tell the time in that semester. Yeah. Was there any other thing that I was supposed to change? Okay, time for the. That's a bad idea to commit directly to master branch, but our main branch. Okay, I do need that extra information for 5 p.m. because I have to change it in Blackboard. I'll do that later.
Okay.
But here, okay, this is not big deal. I mean, Blackboard is the one where you should be able to submit in time. Okay, so actually, I was trying to say that, actually the whole thing started with there is a project. There's a little bit of urgency if you have not really worked on a project. So to really talk to me today, I will try to talk to me today so that I can design it if you have any questions, or if you're stuck on something, or if you don't know what to present, anything is fine. Okay, but you have to talk to me before show up and say, okay, I don't know what to do. Right? And as I said earlier, the actual which teams present on that day will randomize at the beginning of that session. Okay. And generally the questions may take more than 3 minutes. And that's why 7 plus X for questions and some interaction. So you can leave some pointers to interaction if you want, so that there is something to discuss later. Anything else ambiguous about the presentations? It's just, the order will be decided at the beginning. 7 minutes you need to plan for. Do not exceed the time. And I will share a box folder where you will upload. Okay, you can just use those slides that you uploaded will be the ones which will be used for the presentations in both weeks. That's on the logistics. And everybody has to be present. There'll be attendance. Yeah. Anything else? Good. Okay. Yeah, actually try to go to the slides. So today's session is really about, we are really covering a very minuscule quantity of today's topics. But last time we saw, kind of saw some extra aspects of model lifecycle management. And that's where actually there's a lot of activity and excitement these days. Obviously there's a lot of excitement on the model side with large language models and, vision models like Stable Diffusion and DALL-E and so on. But that's the bunch of people building such very, very amazingly performative models. But there's also a lot of people in these companies and also outside who want to consume these models outputs and transform them or expose it to their users, the internal teams, external teams. Right? There are a lot of companies actually just in the span of the last 8 months to 12 months, the number of companies which are focused on AI and AI related processes or products is very high actually. So one aspect of doing that is that they need to know how to manage things, right? Not just model, but also model data, anything else, other artifacts that are kind of part of this process. And last time we saw, I guess 2 weeks ago, we saw versioning, which was MLflow. We saw specific tools, but the tools are not the key things here, although we did discuss MLflow, DVC, and CML. The tools are not the important thing. The important thing is there needs to be, at least for the versioning part, all we want is there needs to be some predictable and transparent and clean way to version your models. Okay, your teams, whichever data science teams, they will be generating lots of models, maybe on their own laptops, maybe on some cluster, and so on. But there has to be some order and some organization to this these artifacts that are being created. Okay, and so that was where MLflow came in. And there's also needs to be order and organization for data. Okay, data gets updated many times in many of our classes. Generally, data is kind of sacrosanct, or whatever the ground truth is ground truth. But a majority of the cases, actually, data gets re-reviewed and re-annotated. Okay, so as long as it's not standard setup, it's not just tabular setup where one of the columns is just a label. For example, images and text. Actually, there's whole teams, as I think I mentioned last time also, there's actually full-fledged companies which supply annotators for you, who annotate, review, and help maintain your quality of your data, right? So you need to version control. I'm speaking loosely here. You need to somehow track your data. Okay, so you could have extra new data coming in. That's obviously one situation, but you might have to relabel your things. Okay, so you might have to, and some of you did object detection stuff last semester. In object detection, actually, it's a huge problem. Other than MS Coco, which also has a huge problem, but MS Coco is one of the canonical data sets used in object detection modeling, at least to show proof of concepts. But even that has a lot of issues, actually. Okay, and there's a lot of time and effort that goes in there. So DVC is one tool that we saw for data version control, because that, I guess that tool's kind of main USP was that you can work very similar to how you work with Git, okay, by storing a .dvc files and this version controlling them, which link to actual data, which could be in cache or some remote location or whatever. Okay, but that's not the only tool. There are many tools that let you version your data. Okay, and lastly, we also saw continuous machine learning. CML is just one tool, but in general, continuous integration is this concept of every time there is a commit of a training script or something where hyperparameters are changed, or some model specification is changed, or some data that was fetched to train the model is changed, or some information is changed in code, it triggers something downstream, okay, which is pick up that model that was trained from that code and test it on some really held out data, which is not access to, which the data scientist didn't have access to, so that there's no data snooping, for example, right? So you can trigger some downstream jobs. For machine learning case, it makes sense to do some testing or validation, like report validation numbers or test numbers or something like that, but also measure things like data drift. How much is the model different from the previous model, right? If it's just a linear regression model, then you can actually literally look at coefficients and how different they are, for example, right? So those types of things, activities can be done in this continuous integration, I guess, pattern. It's a big topic, and I guess software engineers kind of probably know more about it for software tasks, but it makes sense for machine learning as well, increasingly these days. So that was versioning. That was 2 weeks ago. And then last week, we spent a little bit of time on cron and Airflow for scheduling, and just a few comments on A/B testing. Okay, we did not look at any tools last time for A/B testing. We did look at regular testing very briefly, which was through a tool called PyTest. PyTest is, again, not the only tool, just like any of these tools here. PyTest is just one example where how to run tests on your regular Python code. So that's not specific to ML at all, but it's good to incorporate that general Python practice to any code base that you're working on. Okay, anytime you create functions, always think of every function comes with like its twin, or basically not twin, but like a bunch of other functions which test its functionality, so that there is no bugs introduced if you suddenly change something because you learn, because of some update. Okay. So in terms of scheduling, the only last time we tried two things. Cron. I hope if you tried cron, you also did cron tab minus R for removing. Okay. So because if you left it on, as long as the laptop was on, it would keep appending that date information, and the file would blow up. Okay. So I did not show it in the class, but I did remove my cron tab entry after the class. But you guys, if you have tried it, just remove it. So cron was something that's a pretty old tool from 1970s. Just like SQL. SQL is actually pretty old. Okay. Anyway, cron is pretty old, and it makes sense for a single machine. And the same type of interface is also enabled by many cloud vendors also. Like you can literally use the cron type of a specification of how to repeat the job, repeat some training job, data fetch job, whatever it is. And then we saw Airflow, and we saw some that it's a little bit much more complex beast, actually. We just saw its UI. Through this UI, we saw, okay, there's something called a DAG. Many data pipelines or many data, I guess, processes can be kind of broken down into tasks, and you can see the directed relationships between these tasks, and you can run them, and it gets logged by Airflow, and it actually gets logged in for example, a Postgres or some other application database. And there's a nice UI that it kind of shows what's the situation currently. Okay, and this is a tool that's really on the other end of the spectrum, which can work with triggering jobs, not just on the same machine, but multiple machines. And it's actually a whole managed service. In Google Cloud, it's called Google Cloud Composer. It's a multi-million dollar, maybe even $1 billion+ managed service for just Google. Okay, so that's Airflow. So those are things that we saw last time: scheduling and just testing. Not really so much of A/B testing. A/B testing we just discussed briefly. Okay. now today, since this is the last, I guess, demo session, we're going to briefly just talk about some ideas for distributed training. Distributed training or distributed just data processing, actually, not just training. And then we'll look at another kind of family of approaches for large-scale data processing, which is called stream processing. Okay. Within stream processing, I mean, it's a little bit different from usual distributed data processing, where we think of data as living as a batch, as a snapshot, which you move data around and data around potentially a cluster, which is a collection of computers, and to compute something. Like Hadoop is an example of something you might have seen in 561. Spark is something that we'll briefly discuss today. Streaming, on the other end, is slightly different. How it's different is mostly you think of data shuttling between data at rest is not the point of view. Data which is moving is the point of view here, where you think in terms of streams of data moving from point A to point B to point C, where point A, point B, point C are some compute units which will compute, transform the data, and shuttle it forward. Okay, so it's a way to kind of think in terms of some sort of asynchronous parallel processing, because there are multiple units which can compute. As long as the data is ready, they can pull and push, and they can work at their own pace, and so on. So those are the two, although I've separated them out here, but those are the two things we'll briefly discuss. Okay. Any questions of where we are? We've already done just model deployment, and what we did again there are not the only tools. Like TensorFlow has its own serving tool, Torch has its own model serving tool. MLflow has its own model serving tool, right? So it's not that we had to serve models using Flask. In fact, we did not even see many things like authentication and stuff like that, authorization, for actually doing it in a reliable, in a more professional way. But we saw how, some ends of the spectrum, web servers on one end, serverless on the other side, and in between Docker containers, Docker or in general containers. Okay. So any question about like what we've covered in this course? It's not my last point here on the slide is that we have covered very few, basic tools here and there. Among the list of tools that not every data scientist or not every business analyst or not every data engineer has to know. It really depends on which team you're in, which company you're in, and what's the complexity of your models and your stack. But gives you a sense of that this is a big world which intersects with the bigger world of software engineering at some level, right? So at least being aware of that is kind of is going to help you. I think yeah. So let's actually just get to the comments part of this. Okay, let's do it in two parts. I guess the first part, which is the Spark part, will be hopefully a review for some of you. How many of you have not looked at Apache Spark? One. Spark, Apache Spark. You have seen it. You have not seen it. How many of you have seen it? 561. How many have done 561? Good chunk on this side, and only 2 people on this side. You guys have not done 561 yet? Okay. So how come all the senior folks are here and junior folks are on this side, except for like 1 or 2 people here? What happened? I mean, this is closer to the execs, or? Yeah, I feel like there's a trend here, right? Okay, so big data is again a very broad word, and it's been used in marketing and also in technical situations, and in fact the name of the course here. We just want to kind of now just get a sense of the software tooling around the situation where you can't really train or do even processing of your data on a single machine. That's our perspective, right? If you had a single VM or single, your own data scientist laptop or something, and they are hitting the limits, out of memory errors, basically, if they're just doing some data manipulation, transform activities, or if they're training something locally, but it's not, you need to have it needs some working memory, which is like beyond the working memory, or even compute, which is beyond the scope of single machine. Maybe you just need stuff like 8 cores or whatever, 64 cores that typical machines have, single machines have. Maybe you need 10 times that just to kind of speed up the process by 10 times. Maybe it's parallelizable. Like think of random forest, that each tree that you build has nothing to do with the other trees. So you could actually parallelize it quite a bit, right? So maybe in that situation, you don't want to be constrained on the compute side, or in the other case, as I said, not be constrained on the memory side. Okay. The moment you go from a single machine, single virtual machine, single container, whatever, generally containers, by the way, only run on one machine, so it's not distributed. Moment you go from one virtual machine to more than one machine, all sorts of complexities come in. Okay, it's just, if it's possible, just stick with one machine. That's the kind of rule of the thumb, but many times it's not possible. Okay, so why do I say going to a more than one machine to do processing increases complexity? Is because from a program's perspective, all it needs is some memory, some compute, right? Some basically resources like memory and compute typically. The moment, or sometimes network access, like sorry, not network access, but disk access, file disk, hard disk, right? So you want to read a file or write a file or something. Okay. Now, the moment you have things on multiple machines, like a disk, like from the program's perspective, it might want to read a file, and if the file doesn't live on the same machine and it's on the other machine, then there's a network latency involved. Okay, and if the other machine is not right next to it, but in a different data center in a different region of the world, then those files will have bad, will have arbitrary latencies compared to some other bunch of files which are like sitting next to it. Okay, that's just on file access read write side. Okay, but a lot of software, I mean, a lot of software tooling that people build, maybe not specifically Spark, but a lot of tooling people build is to kind of ensure that the programs have to don't individual programs that you write as users, like the Python scripts and so on, they don't have to worry about network access or all that complication. Okay, so it's very similar to like S3, which is a storage service in Amazon. You can put a file, generally like a text file on S3, and there's a very reliable way to access and read and write. But behind the scenes, whether that file is getting replicated, whether that file is not in the same, maybe not in Chicago, but maybe in San Francisco, we don't know, and it's all abstracted away. Okay? Behind the scenes, S3 is a huge, massively distributed system to take care of failures, reliability, latencies, 100 different things. Okay, similar. That's just on something which is on software side, just disk. Here we are concerned with machine learning jobs, data processing jobs, transform jobs, basically extract transform jobs mainly, to be kind of spread out from a single machine to a multiple machine situation. Okay, and there are many tools here. I mean, I just mentioned 2 here. In fact, we'll probably look at the first one only. So Spark ecosystem has been there for some time, which initially was, I think, built in UC Berkeley, and then it was kind of, I guess, moved to the Apache Software Foundation, which Apache, by the way, is the that foundation came from like a web server. Okay, there's a web server called Apache web server. Obviously, there's other, there's actually original meanings for the word, but the web server was the kind of the key software, and then they made a foundation, and now there are a lot of projects, especially related to distributed training, distributed data processing, that are part of that software foundation. And we are interested in the Python API, Python way to kind of speak to and work with this distributed data processing software, and that's PySpark. Many of you might have used, at least folks here, some of you might have used PySpark to play with Spark data frames and so on, and might have also played with something called MLlib. Okay, MLlib is this library which lets you train models in a distributed fashion as well. Okay, not all models are parallelizable. Some models are inherently, by definition, you cannot parallelize them, but some models you can. And so those models are there in the library, not just those models, prediction models, but also other things also there in the library. The Spark tool is also part of several managed vendors like Databricks and others who on Amazon and so on, who add extra UI and authentication, authorization, and many other types of sharing of notebooks or sharing of this script and so on. Those types of things that they add to the Spark software. Okay. There's a similar software called Ray. I don't know, has anybody tried out Ray as a software? It's by a company called Anyscale. Again, I think it's from the same lab in Berkeley, but they have, I guess, a new take on how to do the same distributed data processing and distributed training and so on in a slightly different paradigm. Okay, but we'll just talk about Spark for now. How many of you have seen this figure?
I mean, the full version maybe.
It's from Spark's, I guess, their documentation website. So there's a bunch of things happening here and a bunch of entities. There's a notion of a driver program and something called a Spark context. There's something called a cluster manager, and there are a bunch of worker nodes. Okay, these worker nodes, you can think of them as actually separate machines if you want, and they have some program running called an executor, and that runs bits and pieces of these tasks. Okay, actually, I have a lot of textual description of what these are. Let me see if there is a. Yeah, let me actually not go in the linear way, perhaps, or maybe I should. Okay, let me just do it the linear way. These are just points. I know I could have used figures here, but so what how are we enabling distributed computation, right? So there is some representation of data. Okay, in this case, RDD, or resilient distributed data set, is the abstraction of how a data is represented in this system. Okay, what is the system here? Just think of this driver program residing in one machine, and there are two more machines. Let's say there are three machines for simplicity. Okay, so the three-machine system, and we want to run a collection of. So we want to process some data, and that data is not stored as a CSV file here. It's stored through this RDD representation, distributed across these three machines or two worker machines. Let's say we are only interested in distributing over those two worker machines. Okay, so there is some distributed data. It's not raw CSV file. It's just some representation behind the scenes, which takes care of a few things. And what are we trying to do here is just data processing, which means that there is some starting point data, some original data, okay, split between these two machines, and we want to keep transforming it. Okay, bunch of transformations that we want to do again and again and again. That's pretty much it from a very generic point of view. Obviously, every whatever you were doing, for example, with pandas, right? Let's say you're processing, if you're exploring the New York taxi data set or some other data set, you can do it on single machine if you subsample it, perhaps, or just look at 1 month data. But if you want to look at the whole year data, each month data is like a gigabyte, and you can't look at whole year data on single machine unless you have a lot of RAM, right? So that type of thing, you would be slicing and dicing and removing some, pickups and drop-offs, or looking at prices and aggregating and so on. All that, think of them as transformations, and those transformations are what a typical program would look like. I mean, I was giving just an example of some transportation data set, but that's what I mean by a program that wants to work on data that's split between multiple machines. Okay, and the way to do it is your program will have to obviously use the Spark API, to define appropriate abstraction over this RDD entity, which is called a data frame. And I guess now there's also a dataset API, but let's just call it a data frame, which is just a collection of RDDs behind the scenes. Okay, that data frame is going to look very similar to that single machine experience of working with pandas or some similar objects in other languages also. Okay, Anyway, so that's the setup, and we're just going to briefly discuss what Spark context is and what a cluster manager is, and then what RDD is. Again, okay, it's just a quick recap. So Spark context. So in MapReduce, I don't know if you recall, if you've seen MapReduce, mapping and reducing are like two basic operations, where a map operation is like applying a function on every unit of data, essentially, and then reduce is like aggregating once mapping is done. Okay, whatever the map's results are, you aggregate. Generally, it's a disk write to a disk write to a disk write. Here in Spark, you have memory also in workers that you can use. Okay, so the main application starting point is called the driver program, and in which you create a Spark context. Okay, and that talks to the cluster manager. So we'll look at an example from the Spark's PySpark getting started in a second. So what does cluster manager do? So your program basically has some object that talks to this cluster manager. Cluster manager is the one which is responsible for allocating kind of smaller jobs to each of these executors. Allocating these jobs to worker nodes and calling executors on them. Executors are just programs in the worker nodes which will actually run your tasks. And cluster manager also tracks things. Okay, so each worker node has these executors, those objects that we saw here, this object in orange, and it's a process that runs a Java virtual machine. So Spark is the technology which is behind the scenes is Java, and when it's launched, it obviously has some tracking has to be done so that the original program in the driver program has to know that okay, there's some progress, and we actually processed and did some group by, did some XYZ operations. And basically the executor runs tasks on behalf of the application. Okay. And it can retain data in memory disk storage. So the data is itself represented using RDD. So let's talk about transformations and then talk about the RDD briefly. Tasks are just transformations. So when it says the executor runs tasks are these transformation of RDDs. Okay, this data representation. So what are we doing actually? So we go through the program and look at what is the collection of transformations happening starting from top to the bottom, okay, those tasks, and basically a bunch of transformations and map them into, okay, this is a task, this is a task, this is a task, and therefore basically the driver can say, okay, given these tasks, let's ask through the cluster manager these executors to execute some collection of tasks. There's dependencies between the tasks, and that is also taken care of by the basically Spark context and the cluster manager. Okay, and you can write your program of what you want, what types of transformations you want. You can write it in any language, but it can be dealt with by the executor. Okay, so the language is not a constraint here. Okay, so final comment about RDDs is this is actually, they did not deprecate it, although the dataset API is also there. But RDD is basically the core of this whole distributed data processing software idea. It's just basically, it is a CSV file, or you can think of it as a table in a database, basically, essentially a CSV file, but it has some extra information and some extra things built in. Okay. So what are the extra properties, right? So the extra properties are an RDD is partitioned or sharded across multiple computers or multiple these worker nodes. So each task works only on a part of the data set. Okay? So if there is some operation that requires all the data, then there is some bottleneck in your computation. But otherwise, as long as things are kind of parallelizable, your data resides on multiple machines by sharding, and you can repartition and things like that to kind of move the data around. But essentially, a task, when an executor executes a task, it executes only on a part of the data. typically, if you have large enough data. Yeah.
The partitioning task is taken care by Spark and Club, right? We don't.
Partitioning. There will be a default partitioning, and sometimes if you can monitor cluster load. I mean, you can monitor how much effort each worker is putting. Sometimes the data is not evenly distributed. Okay, through some transformations, the default partitioning that was there, somehow the data, there's more load on one worker compared to other workers and so on. So there's going to be unevening, and so sometimes you may have to call an explicit repartitioning operation, which is again move the data around so that it's well spread out. You could do that. Yeah, but if you don't know anything, by default there's a particular partitioning. There's an external. We're not talking about it at all here, and we'll not probably see it. But there is an external load when you load the data and it's stored in this Spark cluster. Cluster is just a collection of these worker nodes, including the driver node. Then there's some default way in which it's spread out. Yeah.
And the driver and cluster manager together, they're present in the master node.
Yeah. Cluster manager, I don't really know, so I don't know where it's present. Should be in the master node. Yeah, that's the. I don't see any other machine. It will be. Yeah. So as I said, a couple of properties, RDDs. So each task can work on a part of the data set, and so there could be multiple RDDs for the same data set, same CSV file, first 100 rows in one RDD, and so on. But more importantly, RDDs are immutable representations. Okay, so if you do some operation, let's say if you add an extra column, okay, or if you want to do some transformation, you will basically kind of double the memory if you're gonna copy everything and do extra stuff. Okay, so just be careful of that. And the last thing is these transformations are actually lazy transformations. So I don't think I'm mentioned it here, but transformations and RDDs are lazy evaluated in a sense only when it's needed, only when the driver program asks for, hey, show me that data, or I want to download it, the process data, or maybe save it in some application database or something. Only then kind of backtracks and figures out, okay, let's actually compute those transformations, therefore execute those tasks. Okay.
So what is the advantage of this?
Lazy evaluation.
Because
It's saving.
Essentially, you do not even realize that you have made any errors while coding or when programming.
Yeah.
If you don't call your RDD, right?
No, but you're not supposed to debug errors. So you're talking about runtime errors, right? So, lazy evaluation is actually a very important feature. In fact, Pandas doesn't have it, but there's a tool called Dask. I think some team might be doing it. Was it?
The Dask query in Pandas.
What did you say? Dask?
So you mentioned Dask, DX, right?
DASK.
Okay. The number.
So Dask is like a stand-in replacement for Pandas, and the big difference from Dask can also do, by the way, distributed computation if you read its documentation. But generally, the way one of the modes people use it is wherever you use the Pandas script, if it's Pandas script, for example, in terms of compute, Python, if you recall, is like single threaded. Okay, single threaded. So you will be only using one of your cores. If you have 8 cores, you'll be only using 1 core. But if you have, let's say, a group by operation where under each group you're computing something, you could actually parallelize it to multiple cores, and Dask will do it behind the scenes for you. But that's okay. That's just in terms of distribution within a single machine. But Dask does lazy evaluation also.
But what is that?
Lazy evaluation. So you only need results. You don't compute anything till you actually need the results. So it doesn't. It's actually saving you. I mean, if you really want the results, whether you computed before or whether you computed last minute is the same. But if you did not need the results, then it saved you computation. Right. So it's not like it's just because it's lazy doesn't mean you are trading off, like, okay, when I actually ask for the results, it's actually going back and computing, so it's wasting my time. It's not. It's going to take the same time as if you know that you want the results then and there wherever you're calling your transformations or these actions that you're taking on your data frames or whatever, then you can just call .compute and you can actually compute everything whenever you're calling them. There's an extra API there, but if you want results as and when you are calling a statement, then you can also do that. but this is an optional. Yeah, I mean, the transformations are very similar to MapReduce type of mapping, filtering, group by, reduce by, and stuff like that. So for those of you not done anything in Spark or nothing in Hadoop and so on, it'll not sound, it's not clear what's going on. But those who've done it, you should be like recalling like what you did in that course. Okay. So yeah, this figure, I think this figure is just a figure from, I guess, Microsoft's website, where they're just showing like their hosted version of Spark, I guess, software, and what you can do with it. They're just showing how in different parts of your ML pipeline, which is, I guess, data movement, they're showing from ingestion to storing to prepping and training. And then once you prep and train, you might get model artifacts, you serve them. Where does something like Databricks, where does something like Spark cluster, which is, I guess, shown here as Databricks, which is the managed environment, how does it play a role, right? So on the left side, on the ingestion side, is where you would get like CSV files. Maybe somebody gives you CSV files, or you can read a table from an application database, or you can get it from something called Kafka, which we'll see next. Okay, right. So you can get data from anywhere, and then generally you store it in what is called a data lake. I guess this is a very broad term. I think some of you might have even gone through a lecture where they're defining data lakes, but basically, in a one-sentence summary, it's mostly unstructured data compared to a data warehouse, which would basically be like a more structured, warehouse where they've optimized for what queries happen downstream. Okay, and here just showing where some distributed data processing tool or along with its cluster comes in, is where you are preparing data, where you're doing transformations and sending the data back potentially. It's unstructured, you can read it, you can retain structured data in this cluster, or you can send it to third-party locations. Okay, and you can actually do distributed training also. You don't even have to do distributed training. You can also do non-distributed training if you can't distribute. Okay, for example, you can make the worker nodes have GPUs. You can make the driver node have GPUs, and then you can just once you have done some processing of the data in a distributed way, perhaps you can also do single machine computation. So that's not like either or. And then you can just push it, whatever artifacts you create or data you create, you can move it to, I mean, here it's showing as if you get it from data lake and only sending data to data warehouse, but you can also read from data warehouse and also do your training and stuff. Okay. So any questions here? Okay. I think I'll talk about Kafka also, and then we can look at a demo. Actually, I wanted to spend more time giving you guys some time for a projects part. So let me talk about the Kafka, which Kafka is just a tool, but stream processing and stream processing tools, what do they do? And how many of you have never heard of the word stream processing before? How many of you have heard of stream processing before? Before this class, and before like where did you hear stream processing?
Same for the data. I think we have a
Oh, in big data, you also cover stream processing tool?
not the tool, but I mean, we have heard the term, not the exact tool, but
Okay.
essentially, how do you sort of apply ML algorithms
Okay.
to industry?
Okay. So yeah, so streaming is exactly like what you think, like if there's video streaming and stuff like that, right? So stream processing is more about, there's an event or some data stream. Stream, just they really visualize in terms of like a stream of water, like a river or something. And basically that stream of data, you have some intermediate points, compute points, which are potentially ingesting the data, doing some transformations, and just splitting it back to the stream. Okay. And that is something that makes sense where you have a heterogeneous collection of programs or services which are transforming this data. Okay, so somebody might write a program in Go, and somebody might write it in Rust, and somebody in Python. But if they're all like chained in some larger complex, data flow, then they can all work at their own pace, their own ways to interact with the data, as long as somebody else is orchestrating the stream, okay, which is that somebody else is streaming software, okay. And we'll see how an example streaming software, Apache Kafka helps do this behind the scenes task, so that programs can do whatever they can, whatever they do, without minding other issues, okay, other softwares and so on. So just to give you a sense, in terms of one use case, think of a program written in Go and think of a program written in Python. For them to talk to each other, they need to know how each one responds. Okay, are they talking through HTTP protocol? Are they talking to some other WebSocket, or through some other protocol? Okay, so protocol just means like some agreed upon rules through which they can talk to each other. Okay, so instead of every program knowing, like every Go or every Python program knowing how to talk to a Go program, how to talk to a specific Go program, a specific Python program, a specific Rust program, upstream or downstream, instead of doing all that, they need to, in this case, just need to know one way to communicate, and that is with the streaming software. Okay, like Kafka. So let me, I guess, repeat. So software system in a single organization can grow immensely, like a lot of moving parts, a lot of just on the reporting side, there will be so many complications in terms of which data is ingested where, when is data refreshed, when is the report like generated, what is the other dependency on this report. So just on the reporting, okay, we're not talking about data lakes and data warehouses, curation, and actual ML computation. So there are many sources of data, many targets. Targets generally reporting are like ML artifacts that are generated and so on. As I said, and each of these sources and targets, as well as intermediate points, will have their own way of doing things. Okay, the own way of like they may have their own way of storing data, schema for the data, and so on. And they might change also. So this is a problem if everybody has the same, their own ways of doing things, because if the team, agrees on something, that might not be the same as what some other team had agreed a year ago for some upstream or downstream task. Okay, so to kind of manage this, you kind of compartmentalize things, where there's one way in which these softwares can ingest data or output data, process data. Okay, so that is through like this modularization of these data streams. So you really are data centric here, and one of the tools there to kind of enable this, I guess, standardization is Kafka. Okay, so what does it do, right? So it may seem pretty complex so far what I've described. All it's doing is being essentially a middleman. Okay, it's a middleman for everybody to talk to. So if let's say website events are happening and those events need to be logged, there's a service, there's a program maybe written in Rust, which knows only how to talk to Kafka. Okay, it doesn't need to know, oh, I need to actually talk to an application database, I need to talk to some S3. It doesn't need to kind of worry about those things. Okay, so what website events service or something related to that will do is just know how to dump information to, or dump as in like give information to Kafka, this broker. Okay, or this backbone software. And as it says here, it's a distributed messaging system. So it's getting information, this website events, and it's getting this information, and this software itself is not living on one machine, it could be living in multiple machines. But from the sender's point of view, it'll look like, okay, one endpoint where I need to send data, and it'll get the data. And if somebody else needs it, like analytics teams needs it, or the database needs it to store it, it can get the data from this machine, from this backbone software, which again, as I said, could be living in multiple machines. Okay, so this picture is just showing that there are many places from where you can get data, like these are the sources, and many targets which all need to consume this data. And they don't need to know, like, it's not like the database needs to know how to get information from website, from pricing, from finance department or financial transactions, or from sales, or from user interactions. Database doesn't need to know. Okay, it just needs to know how to interact with this backbone messaging system. Okay. Now there is actually a single machine version of Kafka also that you can look at, but we are just talking about the distributed one. Okay, just like for Spark, instead of PySpark data frame, you can always do Pandas or Dask or something else, right? So instead of distributed messaging system, there are actually centralized messaging systems that you can run on a single machine. So that's what this is. Okay, so to demystify, what I'm trying to say is that stream processing is all about being data centric, enabling multiple disparate or heterogeneous processing units or services and services to kind of interop with each other through a kind of a messaging system, okay, which in this case is distributed, and that's why it's a multi-machine situation, which means that this software is running on multiple machines and taking care of all sorts of things behind the scenes, reliability, data replication, and people just need to know how to interact with this one thing, okay? Instead of people as in the softwares need to know how to interact with this one thing. Any questions about the grand scheme of things, like what's going on here? So this is in contrast with a batch processing, or like in the previous case, distributed data processing system, where we're not even thinking in terms of data streams at all, right? So here it's really encompassing more than what like Apache Spark would consider. Apache Spark would probably talk to like a data lake or a data warehouse where there is a table already. Here we're talking about data being generated in kind of continuously, and there are data generators which are at the top, and there are data consumers and transformers and whatever at the bottom, and they run at their own pace also. Just because data is being generated at 100 MB per second at the top doesn't mean all these other softwares below are also working at the same speed. They may be slower. That's okay. The distributed messaging system will take care of it. Okay, this is the asynchronicity part of it. Okay, and you can also do some parallelization here.
It doesn't like sort long data. Based on this picture, it looks like we're just inputting in a long data file, and then it's sort of breaking it down based on the ask.
Yes, that's exactly what is going on. What is going on? It has a temporary way to store the data in essentially a log, and we'll look at that in a little bit more detail.
In fact, the input also, like website events, I'm thinking it'll be like login, a username, password.
Yes.
So what time will they log in?
Yeah.
Price did they pay? What transaction?
Yes. Yes. But that data is not being stored locally. Whatever that service is not storing it locally. It's just sending it to
directly to Kafka.
Yeah, to Kafka for somebody else to consume it. Okay. So for example, if you want to store that data into a database, this service doesn't need to know that there is here's the credentials for this database and who has this and how to talk to that database, for example. This is a MongoDB versus a MySQL, like it doesn't need to know. Right? It can just send that events to some place, and this database will have obviously some way to interact with this Kafka, cluster, and know how to ingest that data into itself every few minutes, for example. It doesn't even have to work at the same speed at which the data is being generated. So I guess that's where this picture is the same picture as before, except now I'm explicitly naming some things as producers. Some apps, these softwares or whatever services that I'm calling, think of them as just programs running on different machines, multiple machines potentially. Some of them are going to be producers, like in each individual's app, maybe on their phone could also be potentially a producer of data, right? The login events that we're talking about. And there are some things which are, called connectors, which are, application databases or things like that. And there are also consumers which consume this information from the distributed messaging platform, in this case, Kafka cluster. Okay. And there are stream processors, are just, tools for kind of transforming these streams. It's just very similar to transforming tables. Okay. And so, why is there a need to process streams? That's more of a software engineering, question. but that's what stream processes are. But for us, the interesting things are mostly producers and consumers. Okay, that's what we saw in the previous slide. So before I get into some detail of how this distributed machine takes care of talking to all these producers and consumers, there are many tools here. Apache Kafka is the name of the open source tool. There's actually same software foundation also has other names, other software like Flink and Storm and so on, which are also open source tools. Actually, Kafka itself was developed in LinkedIn in 2015, I think. Very similar to like MLflow is developed by Databricks, right? So there are different tools which are developed by many of these existing, like Storm, I think was by Twitter. And so some of these big companies have these needs, and that's why they build this software. And so other people are adopting it based on the complexity. So as I said, the rule of thumb is generally to stick with one single machines. If you cannot, then there's going to be challenges. Kinesis and PubSub, I think, are just hosted versions of Kafka. With maybe there's some proprietary bits by Amazon and Google there. So let's look at Kafka itself, right? What is it doing? It's basically there's an incoming request, okay, through some protocol for it to store data. So producers are producing data. So they are asking Kafka to, hey, here's a piece of data for some event that happened for user 1. And here's a data for device 1 or device 2 and so on, right? So the producer is generating data, and Kafka's objective is to store them in what are called, I guess, topics. Okay, so Kafka has a notion called topics, which, as the name suggests, is just a topic-specific log. Okay, it's just literally, as it shows here, it's basically a collection of data points. Okay. It turns out topic is just a table, basically since a collection of record of data points. And in terms of storage, behind the scenes, Kafka stores it as a collection of multiple partitions or multiple small tables. Okay, and one of the properties that will retain is that the elements inside each partition are ordered. Okay, elements across partitions are not ordered. Okay, because it's just chopped the tables in 3 sets. Obviously, in each set, maybe it's the right order in which the events happen, but across sets, it's not the same. There's no ordering that you can get. Okay. So each message is basically each data point, since it's a message processing platform. So each message is basically a data point, okay, from some producer. It could be a record, it could be an event on a cell phone, whatever it is, right? So there's an offset, and you kind of keep writing to it. And then there's some index here, like up to what point the data is. And then if there is a downstream consumer of this data, then they will look at how much the data is, and they'll have their own pointers basically to read the data as in multiple different ways, but to read the data in each topic. Okay, each topic and each partition. Partitions also take care of replication. So the data that is generated the data that is generated is also kind of replicated so that you don't lose data. Okay, if single machine fails. So I guess this is just the same picture that I mentioned. So this cluster, which is a collection of machines behind the scenes, from the user perspective, you don't see a cluster. You just see one location where you want to send data, or one location where you pick up data, but it's a cluster. And inside the cluster, each, I guess, type of data set or data is stored as topics. Topics are stored as actually partitions on multiple machines. Okay. This is what it's doing. It's basically acting as a buffer for data. Okay, in this streaming setup. As I said, so there are some new names, just like there were workers for the Spark cluster. There's a name called brokers for Kafka cluster. A cluster just means a cluster of machines. And here it's called brokers. And each broker will have a certain collection of partitions. Okay. So for example, here is a topic A with 3 partitions. So if topic A has 3 partitions, you could put partition 0, partition 1, and partition 2 in like different machines. And if topic B has 2 partitions, then you can split up these partitions this way. Okay. So here there's no yeah. So okay. So this is how you split the data. Okay. Now, in terms of replication, like if data fails, if one machine fails, what happens, right? So topics are replicated in brokers. So basically, you can see that partition 1 is replicated once, and partition 0 is also replicated once. So in case, for example, broker 102 fails, okay, so let me step back in a second. So by default, data is replicated, but there is going to be a canonical reference to every data point. Okay. So for example, the word leader that you're seeing is the canonical representation of that message or that data point. If that fails, then you can pick up that information from the replicated location. Okay. And same thing with partition 0 has a copy somewhere else. If partition 0 fails, then you can pick up the same data from partition, some other broker. Okay. Yeah. This is replication strategies are not unique to this revision messaging.
Why didn't they just use Hadoop and the web?
Yeah, they have their own way of, so because they need some what is it called, order relationships and some information is, I don't know. Actually, we are not at a level, we are very superficial at this point here. So we can discuss how it's stored, but there is a reason why they have set it up this way.
And there's this one replication because
No, the number of replications in this illustration is 1. You can replicate more as needed. And yeah, they have a leader and a bunch of followers here. Yeah, so leader with a star is just the canonical location of the data. If it fails, and you may think, what's the chance of a machine crashing, right? I mean, sure, machines crash. I know our laptops crash once in a while, but if each machine crashes 1% of the time in a year, and if you have 1,000 machines, what's the probability of some machine crashing in that year? Okay, you can compute that. Okay, it's basically a probability of machine 1 crashing, or probability of machine 2 crashing, or probability of machine 3 crashing. And they're all independent events. That's 1% plus 1% plus 1%, 1,000 times. That means 100% there will be a crash. Okay. So just so that I'm just saying that at large scale, the moment you're going beyond a single machine, a lot of things which you thought were like rare will not be rare. And so that's why these things are important, and you might have looked at in 561. Okay.
So the replication process, is it user defined or is it automatically?
When we create a topic, so we'll actually do a quick demo of Kafka next. When we create a topic, we say how much replication we want, and behind the scenes, it'll, depending on how many machines there are in a cluster, maybe it's infeasible to have, for example, if you only have 3 machines and if you want a replication factor of 4 or something, that's infeasible. So you can take care of this while setting up the topic. So you get to first set up topics. Hey, here's the 100 topics that are possible in my organization. All the producers, all the consumers work with these topics only. Yeah. So yeah. So producers. So you may say, okay, a topic could be like login events on my web app, for example, right? So many people will log in and log out maybe on your web app, over a period of time. You could actually ensure that for a given user, all their login logout information is on the same partition, because you know that on each partition it's actually ordered information. Okay. So to do that, you can pass a key while you're storing your data, so that at least all events related to the key can be saved in the same partition. Okay. So there is some. This is where I was saying that it's not like Hadoop's system. It's just some information that it wants to exploit about order relationships that may be relevant for downstream applications. Okay. So here, I don't think it's not that important. And reading reading of data is, again, once you know that there are topics, you read data in order from partitions from these topics. And so you actually get, for example, if there are 1,000 users spread across 3 partitions, you know that all the events related to maybe 1/3 of your users are actually in this one partition. Okay? So that gives you some, at least processing by, parts. Like, one consumer can process from the first partition, one consumer can process from the second partition, so on. So you can actually do parallelization if possible. Okay. And yeah, here is just showing if you have more consumers than number of partitions, maybe some consumers will be inactive. There is this is an interesting extra software on top of Kafka, which helps manage the Kafka cluster. Okay, so this is all intransient. I mean, maybe so they were actually, if you look at Kafka's page, they were trying to get rid of Zookeeper as a dependency, at least last year and year before. So right now, I think they're in a stage where they might have gotten rid of it, or they're almost, they have 2 versions that they have, where one case you don't have Zookeeper, the other case you have the Zookeeper. What is Zookeeper? Is an extra piece of auxiliary software to manage the cluster. So manage the cluster in the sense, manage the individual machines, which are called brokers. So what does it do? It helps perform leader elections, which means that if a partition is copied at 2 places, let's say replication factor of 1 at 2 places, which one is the leader, which one is not the leader, right? So one of them has to be the canonical copy, and it's all distributed. It's not like you say, hey, this partition in broker 101 is the leader and partition in broker 102 is the follower. It has to be automatically elected, so that if a machine fails, it automatically figures out who's the next leader, and so on, right? So it takes care of that. So it has an intersection with this distributed computing area in machine learning, in computer science, and just maintains, what's the situation with the cluster. Okay? So let's not worry about this auxiliary software, but that's what it is. And let me just wrap up this, discussion here, and we can get into some demo. Is that this is a figure from, I guess, Databricks from several years ago, actually, 2016, which is just showing that Spark itself also can deal with streaming. In fact, Spark streaming is a big feature in the Spark offering. Okay, so although I put Spark in the kind of batch distributed data processing category, which is the previous category, you can actually do streaming also, which means that at the minimum, you can make it obviously a consumer or a producer. You can talk to a Kafka, whatever cluster upstream or downstream, and actually make it a consumer or producer, and actually process data as it comes and so on. Okay, and the way it works is inherently, if you recall, Spark is based on RDDs, and RDDs are like some small subsets of data. So what Spark streaming enables is basically as data comes in, it makes these micro batches of RDDs and does its processing. Okay, so it is still a batch processing software at its core, but it can work with streaming, because the gap between streaming and batch is just the amount of data you're gonna work with at any given point. Okay, so anyway, with that, let's actually look at let's work with Kafka. So what we'll do is maybe not even try Python. So what we're going to do, okay, so before I even get into this, is we're going to just install Kafka, and we'll just try creating a topic, and we'll just use a simple, Kafka gives you an example producer client and a consumer client. And actually, maybe I have a Python script also to kind of talk to it, but we'll just see, we'll submit a message to the Kafka cluster. In this case, it's not even a cluster, it's just a single machine. But we'll create a topic, submit a message to it, or submit some data point to it, and consume the data point. Okay, that's pretty much it. The reason I'm doing this first is because this is newer, I assume, to some of you. Spark is like, it's very similar to Pandas, except the PySpark API has a little bit of differences. But so let's do Kafka first, and do PySpark later. Okay, so any questions of where we're going? I just wanted to ensure that we are all on the same page. Okay, so I think where does it say there is a dependency on zookeeper or not? I want to double check that I'm not getting a version which is not. Okay, let's just pick the latest version anyway. Oh, it's not PySpark. So I'm just downloading it, but you can just download it using any tool. But so I'm just unzipping this unzipping the zip file. So it's like a .zip file, so I'm just unzipping it. So where are we? So this is the unzip folder. So I downloaded this and then why does it say modified 2 months ago? But anyway, okay. So actually let's yeah, sorry, I was looking at the not the introduction, but let's go to quick start. Okay, so actually I could have just showed you this before I did the two operations, but basically you downloaded it, unzipped it using this command tar, because it's a tar unzipped file, and then go into the directory. So this is where I think Kafka has two things. One is with the zookeeper to maintain the health of the cluster versus something else called kraft. But so it says your local environment must have Java 8 plus installed. Let's see if we have it. But let's run the zookeeper service. So Java is not there. So we will install Java. So we can just install Java. Okay, actually, So it's installing Java 11. In fact, not the Oracle Java, but OpenJDK. Oh, sorry, OpenJRE, Java Runtime Environment. But I think that's fine for us. I mean, this is actually a little bit of a bad practice because I'm installing Java on my full system and stuff. Like in Python, how we virtualized and containerized things, we could have done the same here, but I think for simplicity, let's just okay, so it says version, I guess 11.0. So let's actually okay, so we started Zookeeper. I mean, we have to still start the actual messaging, distributed messaging software, Kafka first, Kafka second. So we started this cluster management tool first, and then we'll start the, so for that, you can go here. And the docs just say, okay, open another terminal and just run something else. So if you have some issues with this command, generally there'll be some issues with like memory if you have less memory. Let's see if that's the case, but these are, you know, so what am I doing, right? I'm just calling, there's a shell script, which is just a kind of some sort of wrapper script, which calls an actual program with some configuration parameters. That's all it's doing, okay? The programs are just Zookeeper and Kafka. Okay? Once they're started, then we can talk about, oh, how do I create a topic? And how do I interact with it via Python, let's say on our Jupyter, or via command line, okay? Some firewall. Okay, so now we have started both. Actually, I just want to double check that we already have a Kafka example folder in our MLOps examples. If we do, then we actually do. So this is our repository, which already has a Kafka client example. So we'll just run from there. Okay, so this all has a dependency also, which we don't have installed, but we'll install it in a second. But let's actually let me figure out okay, so I'm in my virtual environment, so pip install. Okay, by the way, I wanted to briefly mention about this pip install XYZ is generally not a good practice. You're literally downloading code from this central repository, but it's not really vetted. I mean, they have been trying to vet it by at least popular packages now. They expect maintainers to have two-factor authentication, stuff like that. But there's actually a lot of tooling that goes into checking that the packages don't have malicious code. Okay, there are full-fledged companies which do that for a fee, and that's an important part. Okay, this whole thing of software supply chain is not just in the software engineering world, but also for machine learning world is important because you could have all sorts of attacks on your models, on your data that might make it behave in a way which will lead to lawsuits. Okay, or could lead to something bad for your company. Okay, so something to be aware of. So I think we need to first create a topic. I mean, here is we're going to create a topic called tutorial topic first, and then we'll add some stuff there. So let's see, how do we create yeah, let's create a topic. This we don't need. So here's how, I mean, there are actually non-command line ways to do the same thing. But here, since we're going through there, getting started, and they're not wedded to Python, they're giving these examples using shell script. We can create a topic using Python as well, but let's actually just create a topic. So remember what I said, like this is a cluster. I mean, right now it's not a cluster, it's a single machine thing. You just need to define a topic when you create it. While defining a topic, you also have to take care of replication. I know somebody was asking. By default, actually, you can see it here. So the way you create a topic is just -create in a shell script. Topic name is quick start events, but you can give any topic, like, any topic name. And then you have to say, where is your server? And so that's, currently it's running locally. So that's why it's localhost and some port. So once you created the topic, you can actually see, describe, -- describe which topic, this topic. If you do that, you actually see that, hey, this is a topic, there's some topic ID. By default, partition count is 1 because we only are on a single machine. So there's literally 1 partition to make. And replication factor is also, I guess replication factor 1 means there's no replication. Sorry. Replication factor 2 means there's a copy. Okay, so that's the information. So by default, it'll see how many machines, brokers you have in your cluster, and as long as you have capacity to kind of create partitions on that, you'll actually get that by default. So let's actually create this topic. May not. Okay, let's just keep it quick start events, but keep going there. But so. This is not the one. Actually, we can just use this one. But for that, I need to go back. Okay, let me just go back. So I didn't want to change the name because that's not won't kind of matter much. So quick start events is the name of the topic. Okay, so let's create this topic. So I mean, the only response is created the topic quick start events. Now let's actually use our example code. So we have 2 example codes here, producer example and consumer example. So producer example is saying we just installed Confluent Kafka, which is the software needed for the Python program to talk to Kafka. Every program, let's say your Go program, your Rust program, will have their own clients to kind of, some sort of client SDK to talk to Kafka. Okay? So all we're saying is configuration, where is the server, where is the Kafka machine, and that's it. And so that's how you create a producer object. And then the topic here is quick start events, if I recall. Yeah. So quick start events, key, as I said, is if you give a key, then if you give the same key again and again, those values, one after the other, will go to the same partition. Okay, here it doesn't matter because it's only 1 partition. So I ran this once. Let's actually, for I in range 10, just add this did not work. I guess, okay, so anyway, I don't know why I turned that color, but I just added a bunch of events, bunch of, I guess, data points into this topic. Okay, now let's actually go to our consumer. Again, the same API, same package, and there's some extra information here, like group ID. This is just if you are in a group of consumers, then you can give some name. There are some extra configurations. Let's not worry about it. And we'll actually probably look at maybe earliest versus something else, but let's create a consumer and subscribe to that quick start Okay. And so consumer.poll, its poll means it's polling this Kafka cluster every with some time interval. So okay, so the first message was value 2. Okay, actually, let me actually go back to the yeah. So this is the API. I mean, value 2 is the first thing that I ran once, and then I had a for loop. So if I do the same thing again, then I get the value 0 and value 1, 2, and 3, and 4, and so on. Okay. So actually, let's go back to the. So this was just to show you the minimal working example of pushing some information to Kafka and getting it back. We can actually read that event, read those things from the machine to see that we did actually, once you read that information, it's not completely removed. Okay, so there is actually some time to live for this data. I think the default is like 7 days or something. So if we query this data, this is what we see. So value 2 was the first time I ran it manually, and then the for loop, which so you can actually, so one consumer already connected to Kafka and read the first 2 values. Now I've created another consumer now from command line is reading the first, all the values. I guess as it's from beginning and read everything means it will read everything. Okay, by default. So you can see 2 consumers consuming from the same thing, 1 producer producing, and you can imagine, producer may be slow, and maybe it's churning through some data and producing 1 aggregate statistic every 5 minutes. The consumer doesn't have to know even what is the frequency at which the producer is producing. Consumer can just keep polling, hey, is there new data? If there's new data, let me pick it up. Okay, if consumer is faster, right? So this asynchronicity is pretty helpful in the moment you have like too many teams working on too many different moving parts, and they have to talk to each other for data pipelines. So any questions here? I know I did a little bit of faster demo, but okay, no questions. I want to see where the oh wow, it's already 8:11. Okay, let's take a break for till 8:29 minutes, and then I think instead of doing a Spark demo is very similar. You basically it's like pandas, except you pip install PySpark. Otherwise, it's the same. So instead of doing a Spark demo, I want to give time, at least 40 minutes, for teams. If you're stuck on something, if you're not clear on what you want to do for the project or for the presentation or for the report, you can talk to me separately as well. Okay. So let's do that. So let's take a break till 8:20 or 8:22, and then convene.